Welcome to today's class on functional analysis. Today we discuss characterization of Banach spaces in terms of a summable series. So first we define a summable series. Let xn belongs to x for n equal to 1, 2, 3, etc. We say that the series sigma n equal to 1 to infinity xn is summable in x if the sequence Sm of partial sums given by Sm is equal to sigma n equal to 1 to m xn converges in x. If Sm converges to S in x, we write S equal to sigma n equal to 1 to infinity xn. And we say that S is the sum of the series sigma n equal to 1 to infinity xn. Now we define absolute summable series. A series sigma n equal to 1 to infinity xn is absolutely summable if sigma n equal to 1 to infinity norm of xn is less than infinity. You can write as a remark. We know that every absolutely summable series in K is summable. We know that every absolutely summable series in K is summable. Now we are going to give a characterization. This theorem 8.1. So this is actually a characterization for a Banach space. A normed space X is a Banach space if and only if every absolutely summable series of elements in X is summable in X. Now we prove the theorem. Proof. Let X be a Banach space. Suppose sigma n equal to 1 to infinity xn be an absolutely summable series in X. That is, xn belongs to X and sigma n equal to 1 to infinity norm of xn is less than infinity. Then the sequence Sm of partial sums is a Cauchy sequence in X. Since norm of Sm plus j minus Sm, this is equal to Sm plus j is x1 plus x2 plus etc plus xm plus xm plus 1 plus etc plus xm plus j minus x1 plus x2 plus etc plus xm. So this is equal to norm of xm plus 1 plus etc plus xm plus j, and this is less than or equal to norm of xm plus 1 plus etc plus xm plus j for m equal to, for all m equal to m, j equal to 1, 2, etc. Therefore sequence Sm is a Cauchy sequence in X, and since X is complete, Sm converges in X, that is sigma n equal to 1 to infinity xn is summable. In X. So we have started with an absolutely summable series. We have seen that it is summable. So this proves the first part. Now we prove the converse. Conversely, let a very absolutely summable series be summable in X. Let Sn be a Cauchy sequence in X. So let m1 be a positive integer such that norm of Sm minus Sm1 is less than or equal to 1 for all m greater than or equal to m1. Since Sn is a Cauchy sequence, this is possible. Now you define inductively m2, m3, etc. such that mn less than mn plus 1, and for all m greater than or equal to mn, norm of Sm minus Smn less than or equal to 1 by n square. Let xn equal to Smn plus 1 minus Smn for n equal to 1, 2, etc. Then sigma n equal to 1 to infinity norm of xn, that is equal to sigma n equal to 1 to infinity norm of Sm n plus 1 minus Smn. So this is less than or equal to sigma n equal to 1 to infinity 1 by n square, since mn plus 1 is greater than mn. Therefore, sigma n equal to 1 to infinity norm xn is less than infinity, because this is summable. Therefore, sigma n equal to 1 to infinity xn is absolutely summable. Therefore, sigma n equal to 1 to infinity xn is summable by our hypothesis. We have Smn equal to Sm1 plus sigma j is equal to 1 to n minus 1 xj. This is because Sm1 plus sigma j is equal to 1 to n minus 1 xj is Sm1 plus x1 plus x2 plus etc. plus xn minus 1. So this is equal to Sm1 plus x1 is xn is Smn plus 1 minus Smn. So x1 is Sm2 minus Sm1. x2 is Sm3 minus Sm2. etc. Xn minus 1 is Smn minus Smn minus 1. And you can see that this cancels with this one, this cancels with the next one, this one. Sm3 will cancel with the other one. The Sm minus 1 will cancel with the previous one, etc. So this is Smn. So this is the reason. So Smn is Sm plus 1, Sm1 plus sigma j is equal to 1 to n minus 1 xj. Therefore, the subsequence Smn of the Cauchy sequence Sm converges in X. Therefore, Sm converges in X for X is complete. So this proves the theorem. That's all for the day.